what if you do have a general list of numbers in the box? What then? Well, if the sample size is really big, okay, so first, let's back up slightly. This, pretending that p is a half to get a worst case scenario here, can be very, very pessimistic, or it can be about right. It depends on whether the true value of p actually is really close to a half or is close to 0 or 1. Okay, if it's close to 0 or 1, then this is going to be really crude. And if it's close to a half, then this is going to be really good. That, we're all together? All right, if we had a really big sample, then our estimate of the sample percentage would likely be, our sample percentage would likely be a pretty good estimate of the population percentage. It would likely to be pretty close to the population percentage. So if it is close to the population percentage, then the SD of the box would be close to what I would get if I plugged in the sample percentage in place of the population percentage here. Okay, so I'm going to say, suppose that my estimate is I'm going to use a Greek letter phi for the sample percentage. So this is the number of the ones in the sample divided by n. Okay? So that's our estimator. It's an estimator of the population percentage. And if phi is close to p, then the square root of phi times 1 minus phi is close to the SD of the box, right? Because the SD of the box is p times 1 minus p, okay? So this number is called the bootstrap estimate. Of the SD of the box. Okay, it's called a bootstrap because you've heard of the notion of pulling yourself up by your bootstraps? Okay, like how do you get up with nothing to stand on? You pull yourself up by your bootstraps. Okay, how do you figure out what the SD of the box is when you don't know what's in the box? Well, you pretend that the sample is what's in the box. And then you pretend that the sample percentage is the true population percentage, in which case this would be the SD of the box. Okay? This estimate is not likely to be very good if the sample size is small. If the sample size is big, this is likely to be a pretty good estimate. If the sample size is small, like 3, 5, 10, something like that, it's probably not very safe to use this as the estimate of the SD of the box. You should stick with the worst case estimate, pretending that p is 50%, okay, which will give you something conservative. But if the sample size is 100 or 1,000 or 5,000, then the sample percentage ought to be pretty close to the population percentage, and the bootstrap estimate of the SD of the box ought to be pretty good estimate of what's actually in the box, the standard deviation of the box. This all right with everybody? Yeah. Little n is the sample size, right? This is the sample percentage, so it's how many ones are there in the sample divided by how many things you looked at. Okay. So far, so good? Okay, this this bootstrap estimate of the SD of the box, I think I'm calling S star. Yep. Okay. So we're calling this thing, the bootstrap estimate is going to be denoted S star. S star is the square root of the sample percentage times 1 minus the sample percentage. Okay. All right. This idea of pretending that the sample is like the population in order to figure out what the SD of the population is like in order to figure out what the standard error of your estimator is, right? So the next step from here, having estimated the SD of the box to be this, we could now use this to give an estimate of the mean squared error, an estimate of the standard error of the estimator, right? What would our estimate of the mean squared error be based on this? We know that the sample percentage is unbiased, so we don't need to worry about this term. This term is 0. But our estimate of this term would be what? Okay, so for the sample percentage of a simple random sample as an estimate of the population percentage, what do we know? That the bias of that estimator is 0. The standard error of the estimator is equal to f times the square root of p times 1 minus p over root n. And we know that that is less than or equal to f times a half over root n, right? Because we know that this can't be bigger than a half. And we know that if the sample size is large, then this ought to be about the same as p. And so the SE of the sample percentage ought to be about f times sample percentage 1 minus the sample percentage over root n. Okay? So this is what it really is, but we don't know p. So we don't know what it really is. No matter what p is, it can't be bigger than this. If our sample size is pretty big, then it ought to be pretty close to this. This all makes sense? Okay. Now, this move of saying, I don't know what's in the box, but I'm going to estimate the standard deviation of what's in the box by the standard deviation of the sample, right? That I can do even if the box has numbers other than 0 and 1 in it, right? That doesn't rely on the numbers in the box being only 0 and 1. What we needed for that was to get this upper bound. But this approximation isn't relying on the fact, the idea of taking, this is the SD of the sample, right? The SD of a list of zeros and ones is the fraction of zeros times, fraction of ones times the fraction of zeros, square root of that. Yep. Okay, so, so I didn't quite close the loop here. What would our estimate of the mean squared error be then? We know it's not bigger than this thing squared. And if the sample size is big, it ought to be about this thing squared. Right? That's what it's this term that we're worrying about.